I've said it before, and I'm going to say it again. When we're working with limits, we want to find values very, very close to C, and not necessarily the value at C. Sometimes that value at C is going to be a great indication of what our answer is going to be, but when we've got the wholes or the asymptotes, we can't trust that that's going to be our value. So we want to look at values very, very close to C and not necessarily the values at C. And we can clearly see that when we deal with piecewise functions. Here, f of x is equal to 1 when x is not equal to, and equals 0 when x equals 2. So we've got a graph that looks like this for our piecewise function. At x equals 2, we are 0. When it's not equal to 2, then we're equal to 1. So I want to know, what is the limit as x approaches 2? So I want to know the limit as x approaches 2 of f of x. Once again, I want to know what is happening very, very close to my point of interest, which is 2 in this case. I want to get very, very close to the C value, and not necessarily what happens at C. So here's x approaches 2, what happens. So what's happening at 1.999 or 0.9999? And if I were to be at 1.999, my value is 2. If I'm 1.99999, actually I take that back, my value is 1. If I'm at 1.999, my value is 1. If I'm 1.9999999999999999999, I'm 1. So it doesn't really matter except for when I'm at 2 itself, I drop to 0. So my limit is going to be 1. As I get very, very close to my x approaches C value, or in this case 2, what is my y value? What is my output? And my output is always 1 unless I am right at 2 there. Now there are some situations where limits don't exist. The first is when the left-hand and right-hand limits are not the same. Example here, find the limit as x approaches 4 of the absolute value of x minus 4 over x minus 4 graphically. If I were to graph this, my graph is going to look something like this. And here, the limit does not exist. If I find the limit as x approaches 4 from the left of the absolute value of x minus 4 over x minus 4, I'm going to be at a negative 1. But if I look at the limit as x approaches 4 from the right, x minus 4 over x minus 4, I'm going to be a positive 1. So right there, my left hand and my right hand limits don't match up. So the limit of a two-sided limit here, this does not exist. We really want to be careful when we have absolute values, because absolute values naturally lend themselves to be plus or minus versions. The second thing is oscillating behavior. Here, finding the limit as x approaches 0, the sine of 1 over x graphically. If I were to graph the sine of 1 over x, I know I'm going to have an issue at 0, because if I plug in a 0, 1 over 0 is undefined. So the sine of an undefined answer, I really can't find a value for that. If I look at my graph, it seems to be okay, and then all of a sudden I get all the squiggly stuff in the middle before I go back off again. When I see all that squiggly stuff in the middle, that's oscillating behavior. And if I keep zooming in, no matter how many times I zoom in on my calculator, I'm just going to see more and more lines going back and forth. I never converge, or I never come to a specific point that I can find a limit of. So anything that's got these squiggly oscillating lines, we're going to have a limit that does not exist. Finally, when we're dealing with infinity and asymptotes, I know right here the limit is x approaches 2 of 1 over x minus 2 quantity squared. I'm going to have a vertical asymptote at x is equal to 2. And if I graph this, my graph is going to look something like that. This is what we call unbounded behavior. when we go off to infinity, either in the positive or negative direction, we've got unbounded behavior. And unbounded behavior itself, you aren't coming to a specific point. You're going off forever. So we really don't have a limit that as x approaches c, what do I get closer and closer to? But one thing we do like to designate is when we're going off to positive or negative infinity. So the limit as x approaches 2 from the left, we like to just indicate that we're going to positive infinity. And then the limit as x approaches 2 from the right, f of x is also positive infinity. But unbounded behavior itself does not have a limit. You're not going to a specific output value. Your output value is always changing. It's just going off to infinity forever. But we still like to designate that we are going off to infinity, either in the positive or the negative direction. So if you watch all these videos, you should be able to describe the limits in actually 3 of the 4 ways, not all 4 ways. But you could probably figure out that 4th way, the algebraic way, just from what we've done with the tables. But we specifically talked about graphical, where we look at the graph and say what value do we approach from y as we get closer and closer to our c value. What y value do we get? We've looked at it from the table perspective, where when we know our c value, we plug in values very close to c on both sides. We've done it from the verbal perspective, where we talk through as x gets closer and closer to c, what does y get closer and closer to. And then algebraic is when you would plug in values in for x to see what you get closer and closer to, which you actually did early on, but when the values were defined. So that's our summary of limits for this first lesson.